All right, let's dive into the never ending, high stakes battle for our digital identity. Seriously, it's this fascinating cat and mouse game between the people building the locks for our digital lives and the people who are constantly, always trying to pick them. It all really boils down to this one simple idea. Your password is like your key. Simple enough, right? But what happens when the blueprints for millions upon millions of those keys get stolen and just dumped online for anyone to see? That question right there is at the heart of this entire game. So here's where we're headed today. We're going to start with the fundamental password problem. Then we'll look at the first big countermove, cracking the code. From there, we'll peek inside the attacker's playbook, see how they evolved to stealing your digital ID, and finally, we'll look at what's next in the passwordless future. It's a whole story of moves and countermoves. Okay, first stop, the password problem. This is our oldest, most familiar line of defense. But here's the kicker. Its biggest weakness? Well, it isn't technical at all. It's us. It's human. Just look at this number. It's absolutely staggering. Something like 85% of us reuse the same password across a bunch of different websites. I mean, we all do it, right? It's just convenient. But that one habit is also the single biggest crack in our digital armor, and it creates a massive, massive opportunity for attackers. So, to fight back against this, the security world came up with a really clever defense. The idea was simple. Even if a company's entire database got stolen, your password should still be safe. And that brings us to the first major defensive move in this game. And that defense is called password hashing. Now, here's the golden rule, the most important rule. A website should never, ever, ever store your actual password. Instead, they run it through this process that basically turns it into a long, scrambled, unrecognizable string of text. That's called a hash. That is what they're supposed to store. Now, to really get this, let's just forget about code for a second and think about something a lot more familiar. A magical blender. Trust me, this simple analogy is just a brilliant way to picture how hashing really works. So here's how it goes. You take your ingredients, that's your password, and you drop them into the blender, which is the hashing algorithm. You hit blend, and out comes this totally unique milkshake, and that's your hash. Now here's the magical part. You cannot take that milkshake and turn it back into the original ingredients. It's a one-way street, a one-way process. And this one-way street idea is the absolute core of its security. I mean, even if a hacker steals the entire database of these milkshakes, they can't reverse them to get the passwords. At least, that was the theory. But of course, the attackers, they found a weakness. And a perfect real-world example of this is the infamous LinkedIn breach. So, back in 2012, millions of these password hashes were stolen. Fast forward 4 years, and suddenly the full list of 117 million accounts pops up for sale online. So, what happened? How did hackers crack these supposedly unbreakable hashes? What ingredient was missing from the blender? Well, the problem was a missing ingredient: salt. No, seriously, LinkedIn wasn't salting their hashes. Salting is just adding a unique, random piece of data to every single password before you blend it. See, without that salt, the password123 creates the exact same hash for every single person who uses it. And that predictability, well, it allowed hackers to build these massive pre-calculated lists called rainbow tables to just instantly match common passwords to their hashes. This weakness just blew the doors wide open for a new, super efficient kind of attack. It's one that plays directly on our habit of reusing passwords all over the internet. So let's take a look at the attacker's playbook. Okay, so you've got two main types of attacks here. A classic brute force attack is kind of like trying every single possible key on one single lock. It's loud, it's slow. But credential stuffing, that's way different. It takes a known list of usernames and passwords stolen from one place, like LinkedIn, and just methodically, automatically tries them on tons of other sites. Your bank, your email, you name it. It is a pure numbers game that works only because we reuse our passwords. Now, you might look at the success rate for this, it's around 0.1%, and think, that's it? That's incredibly low. It seems almost pointless, right? But this is where the sheer scale of it all changes everything. Let's say you have a list of just 1 million stolen accounts, which by today's standards is tiny. That 0.1% success rate suddenly becomes 1,000 successfully hacked accounts. And attackers are working with lists that have billions of credentials. The math, well, it gets very scary very fast. So, as more of us started using better passwords, using things like multi-factor authentication, the attackers did what they always do. They adapted. They shifted their focus from stealing the key to stealing something way, way more powerful. So let me ask you this. You use MFA, right? That little code you get on your phone? That means you're totally safe from these password attacks, doesn't it? Well, not exactly. The next phase of this cat and mouse game involves bypassing MFA completely by stealing your authenticated session itself. And they do this by stealing something called an authentication token. You can think of a token as basically a digital receipt that you get after you've already logged in and proven who you are. This little receipt is what keeps you logged into a website, so you don't have to type your password and MFA code every single time you click a new page. Let's make this even clearer with an amusement park analogy. A really powerful, long-lasting session token, that's like your all-day season pass. It proves you belong in the park and can go anywhere. Then you have these little access tokens, which are like single-ride tickets. They're temporary, they're only good for one specific thing. Attackers, they don't care about the single-ride ticket. They want to steal your season pass. And stealing that season pass is surprisingly easy. Malware on your computer can literally just copy the token file. It can be snatched right out of the air if you're on unsecured Wi-Fi. It can even be pulled from a company's own server logs if they're not careful. An attacker just needs to make a photocopy of your season pass. And to the website, both the original and the copy look totally legit. So this huge threat of token theft has basically forced the entire industry to develop the next generation of defenses. The goal now is to build a system where there's no password to steal in the first place and where a copied token is completely and utterly useless. And the next evolution here is the passkey. The difference is really simple, but it's profound. A password is a secret that you know. It can be stolen from your memory or from a database. A passkey, on the other hand, is a cryptographic key that is tied to a device you own, like your phone. There is no secret for a hacker to steal from a server, which makes it way more secure and really resistant to phishing attacks. And to solve that token theft problem, we've got something called token binding. This is the direct counterpunch. What it does is it cryptographically locks your token to your specific device. So let's go back to our analogy. This is like putting your photo ID directly onto your season pass. Even if a thief manages to steal it, the right operator is going to look at it, see the photo doesn't match, and deny access. A stolen token becomes worthless. You know, this cat and mouse game of digital identity is never really going to end. We're developing these incredible new technologies like passkeys and token binding, but it all raises one final, really important question. As the locks and the lockpicks get more and more sophisticated, will our most critical line of defense always be a human one, our own vigilance? Something to think about. Thanks for tuning in.